Hello everyone. So in this one shot, I'm going to cover semiconductors. So I will cover all concept as per the syllabus. So first have a look at the syllabus. So first we'll see the concept of energy bands. So then we'll see the energy band diagram in conductors, semiconductors and insulator and how the conduction is happening in all these three. Then we'll see the different types of semiconductors. First we'll study intrinsic semiconductor and then the P and N type semiconductor. Then the concept of PN junction, how it can be formed. And then the IV characteristic in case of a diodes. So in forward biased as well as in the reverse biased mode. And then the application of junction diode, that is the diode as a rectifier. Let's start. How we can define semiconductor? So there is a crude definition. We can say the conductivity of the semiconductor lies between the metals and the non-metals. So I can say the conductivity of metal will be greater than the conductivity of semiconductor, and that will be greater than the conductivity of non-metals, right? So, and how the conductivity changes if we increase the temperature of semiconductor? As we know, in metals, what happens? If you increase the temperature, the resistance increases, conductivity decreases, but that is not the case in semiconductor. If you increase the temperature, the resistance decreases and the conductivity increases, right? So we can say in case of semiconductor, the thermal coefficient of resistance is negative. So negative thermal coefficient of resistance, right? So we can say as temperature increases, the conductivity increases in case of semiconductors, right? So that is the property, right? So if you increase the temperature, conductivity increases. Right, and there are certain methods with which we can alter the conductivity of semiconductors. So that is the reason we use them extensively in all electronic devices, because we can alter conductivity. So there are various ways. One will be by giving energy with the form of photons, or by changing the temperature, or by replacing some of the semiconductor atoms with some other atoms. We'll see in extrinsic semiconductor, if we replace silicon with aluminum or silicon with phosphorus, we can alter the conductivity, right? So to understand that how the conductivity is changing, we should understand how the electron is bonded to the atom. So let's see. So in an isolated atom, what is happening? So we have a nucleus and there is a single electron, let us say, which is orbiting around the nucleus. So when we have two charged particles interacting with one another, there has to be some potential energy. So do you know what is the formula of potential energy? Yes, we all studied that in electrostatics. If there are two charges, then the potential energy of the system is given as K Q1 Q2 by R, where R is the distance between the two charged particles. So here we have a positively charged nucleus and there is an electron which is orbiting around the nucleus, right? In a fixed energy level, let us say. And there is a Coulomb attraction, and due to that it is able to move in a circular path. Now if we plot the graph of potential energy with the distance from the nucleus, let us plot the graph. So on the x-axis I'm showing the distance, and on the y-axis I'm showing the potential energy. And since electron is negatively charged particles, the potential energy will come out to be negative. So if I plot the graph, it will look like this, right? On both sides of the nucleus, to the left, to the right, the graph will look like this. Can you see, as the distance of the electron from the nucleus increases, the energy also increases. So as R increases, U also increases. So I can say if we have a 1s orbital, the energy will be something like this. So this is R for 1s, and this is the energy of 1s orbital, right? U of 1s. Similarly, as we increase the distance, say this is 2s, right? R for 2s, and this will be the energy for 2s. So like this, the energy is increasing as we increase the distance. Now this is a very simple situation. But what happens if we have two atoms? If I show the orbitals, so this is 1s, 2s, 2p for the first atom, and this is 1s, 2s, and 2p for the second atom. Now let us see, there is a common point on 2p, right, for both the atoms. So this, let us consider this point is A. Now this point is equidistant from both the atoms, right? So its distance, let us say, is R from both the atoms. So we can say if the electron is at A, it is equally attracted by both the nucleus. If that is the case, we can say this electron can move from one atom to another atom. Or if we consider an electron which is in an orbital which is having energy greater than 2p, then that atom is again bonded with both the atoms. So the electron which is in 2p of first atom, it can move from one atom to another atom. So this electron can move from one atom to another atom, and like this it will take part in the conduction process. So such electrons are known as conduction electrons. So I can show this in this diagram. So the electrons which is having energy greater than, let us say, this 2p energy, they will take part in the conduction process. And this band, kind of a band, so we have a range of energy. So when we have a range of energies, it is called a band, and this band is known as conduction band. Okay, so again it is a simple case, but what happens if we have a lattice which has trillions of atoms? So let us see. So in a lattice, again we can say the electron which is having sufficient energy, they can move from one atom to another atom and take part in the conduction process. So I'm taking an electron which can move from one atom to the another atom and can move throughout the lattice. So if you exert some external field, let us say, then the electron will experience force opposite to the electric field and they can move in that particular direction. So let us say if we exert an external field in the right direction, the electron, a conduction electron, will move in the opposite direction and take part in the conduction process. So the shaded band, this band is again a conduction band. So that we have to remember. Okay. So here a single electron is bonded with multiple atoms or multiple nucleus. So in isolated atom, we have discrete energy levels, but if we have more than one atoms, then the discrete energy level system will be violated, will be having bands instead of discrete values. So I can show it like this. Let us say this is 1s orbital, this is 2s, 2p, 3s, 3p. So 1s will be having a range of energies which is known as a band, right? So this will be 1s band, 2s band, 2p, 3s band, 3p band, like this. So let us take an example of sodium, right? So in sodium, if I write down the electronic configuration, it is 1s2, 2s2, 2p6, 3s1. So we can say 1s orbital is completely filled, 2s is filled, 2p is filled, right? And 3s is partially filled. So if I take a hypothetical scenario, let us say at 0 Kelvin, right? At 0 Kelvin, the maximum energy possessed by the electron is what? I can say this is the maximum energy, right? Possessed by the electron. Now this energy level is known as Fermi energy level. So at 0 Kelvin, maximum energy possessed by an electron is called Fermi energy, right? Okay, so what happens? Suppose if we increase the temperature. If we increase the temperature, then there will be electrons which will be having energy greater than Fermi energy level. So as temperature increases, electron energy, so there will be some electron which will be having energy greater than Fermi energy. And if I consider the valence shell, this 3s orbital, right? So the electrons which is having energy in the 3s orbital, those electrons are known as valenced electrons. And the energies of valence electron constitute another band which is known as valence band. So valence band, it contains energies of valenced electrons, right? So you must be wondering why we are studying these band diagrams and how we can compare conductivity of metals, non-metals by understanding these bands. So let us see. So let me first start with the metals. So in metals, if I show the conduction band and the valence band, so this one is, the yellow one is the conduction band and the white one is the valence band. Can you say there is a overlap? So we can say there is a overlap in conduction band and valence band. So what does it mean? So there are already electrons in the valence band which are taking part in the conduction process, and there will be some electrons which are not in conduction band, but they will gain energy can easily move to the conduction band and take part in the conduction process. So we can say in metals we have large number of conduction electron, hence the conductivity is huge. But what happens in non-metal? So in non-metal there is no overlap, right? No overlap. So there is a gap, and this gap is known as forbidden energy gap. Forbidden energy gap, or we can also call it a band gap. So, and this delta Eg in case of non-metal is greater than 5 electron volt, and it will be very difficult for the electrons to gain this energy from the temperature, right? So they cannot attain this energy if you increase the temperature. So that's why there are hardly any electrons which are in the conduction band which can take part in the conduction process. So that's why the conductivity of non-metal is poor. So you can say hardly any electron in conduction band to take part in conduction process. Take part in conduction process. So that we have to remember. Now let us see what happens in the semiconductor. So in semiconductor still there is a gap, but this gap is not as huge as the case in the non-metal. This gap is less. So here the delta Eg is less than 2 electron volt. Now the electron, they can attain energy at room temperature and they can jump to the conduction band. So the electrons in the conduction band can increase at the room temperature, or even if you increase the temperature beyond room temperature. So what is happening here? So when electron moves from the valence band to the conduction band, we have free electrons or conduction electrons which can take part in the conduction process. And there is one more thing happening in semiconductor. When electron jumps from valence to conduction, there is a vacancy created in the valence band which is known as hole. So there is a vacancy. Hole is the vacancy created in valence band when electron moves to conduction band. We'll see in the later part of the video, these holes will also take part in the conduction process. So in semiconductor, conduction happens in two ways. One by the free electrons in the conduction band and the holes in the valence band. So here conduction happens in two ways. First by free electrons in conduction band. Second, holes in valence band. Okay, so now let us see the different types of semiconductors that we have to study. So we can categorize semiconductor as intrinsic and extrinsic. What are intrinsic semiconductors? These are pure semiconductors. Pure semiconductors like silicon, germanium, etc. Right? And what are extrinsic? So what are extrinsic? Basically, if you do some addition of impurities, if we add some impurities to a pure semiconductor, we'll get a extrinsic semiconductor. So we can say pure semiconductor with added impurities is called extrinsic semiconductor. So we'll study two types of semiconductor, two types of extrinsic semiconductor. One is N type, another is P type. How we can form N type? We can form N type by using pentavalent impurities like phosphorus. And we can form P-type semiconductor by using trivalent impurities, say aluminum, right? Okay, now let us see what is an intrinsic semiconductor. So a single silicon atom is bonded with 4 neighboring silicon atoms. So if I consider this silicon, it is bonded with 1, 2, 3, and 4. Now what happens as the temperature is increased, some bonds will break. So as the temperature increases, some bonds will break. So let us say this bond breaks first, right? If this breaks, let us say this electron will come out. Now this electron will move to the conduction band. And when bond breaks, there is another thing happening. There is a vacancy created, right? So here we have a hole. A hole is being created. Let us say there is an electric field which is applied in the upward direction. Now, due to this electric field, there will be a force experienced by the electron in the opposite direction. So that is the force experienced by the electron because of the external field. And let us say now this bond breaks. Now, when this bond breaks, this electron, it will occupy this vacancy. So if it occupies this vacancy, then the hole will move in this direction. Now this becomes hole, right? Now, let us say this bond breaks. If this bond breaks, so this electron, it will occupy this hole and the hole will migrate in the opposite direction, and the hole moves in this direction. Now let us say this hole breaks. This bond breaks. So if this bond breaks, then this electron will occupy this hole. And we can say the hole will move in this direction. So like this process keeps on happening. So can you see the motion of the hole? The holes are moving in the direction of the field and the electrons are moving opposite to the direction of field. So we can say inside the intrinsic semiconductor, we have two types of currents. One because of the electrons which are in the conduction band, and other due to the motion of holes which is in the valence band. So we can say there will be a current IE which is because of conduction electron, and there will be a current IH which is due to the holes in the valence band. So that we have to remember. So the overall current in the metal or in the conductor, so not metal, so overall current will be IE plus IH. So that we have to remember in case of intrinsic semiconductor. I hope it is clear. So if I say Ne, that is the concentration of free electrons. So this is the concentration of free electrons, and NH is concentration of holes. Usually concentration is measured like this, say 10 raised per 19 per meter cube per unit volume, right? So and Ni is concentration of intrinsic charge carriers. Okay, concentration of intrinsic charge carriers. So in semiconductors, there is a relation of between these three physical quantities. So it will be Ni is nothing but the square root of NeNH. So this relation we have to remember, and it is applicable whether we have a pure semiconductor or doped semiconductor. Now let us see the example of N-type semiconductor. So in N-type semiconductor, what we have done, we have replaced some silicon atoms with phosphorus, which is pentavalent. So we have pentavalent impurity. So we are using phosphorus. Now phosphorus has 5 electrons in its valence shell, and 4 of these electrons will be used to make bond with the neighboring 4 silicon atoms. So we have neighboring 4 silicon atoms. So it will form bonds with these silicon atoms, and the 5th electron, which is loosely bound to the phosphorus, can be released to the conduction band even at room temperature. So the 5th loosely bound electron can be released at room temperature to conduction band. Now, the generation of electron is happening in two ways. So generation of electrons happening in two ways. So first, we can say some of the electrons will be donated by the phosphorus. So donated by phosphorus, which is our donor atom. And second, intrinsically, right? So when bond breaks, we'll be having some electrons, free electrons, which will move to the conduction band intrinsically. So due to these two ways, the concentration of electron will be very large in comparison to holes. So we can say Ne will be large in comparison to hole. And there is one more process happening, which is known as the recombination of electron with the hole. If we consider recombination process, the concentration of hole will further go down. Will further go down. So we can say the concentration of electron will be very large in comparison to hole. So the majority of the electrons will come from where? It will come from the phosphorus. So we can say if we have Nd, Nd is the concentration of phosphorus atoms. So we can say this is the concentration of donor atoms. So we can say Ne will be nearly equals to Nd. So if Ne is nearly equals to Nd, then if we want to find the concentration of holes, we can use this formula. Ni is equals to root of Ne times Nh. So Nh will be Ni square divided by Nd, because N is nearly equals to Nd, right? So we should remember this. So usually what type of question can be asked? Will be given Ni, right? Will be given Nd, and we have to find the concentration of the hole. I think this concept is clear. Now let us see the band structure in N-type semiconductor. So here we have conduction band, this is valence band. Now we know that there are some loosely bound electrons with the phosphorus atom. So, and they will move to the conduction band with a small amount of energy. Now there will be a new energy level created between these two bands, and this energy level is known as donor energy level, right? So the electrons which are in this, so these are, it contains the energy of the electrons which are bonded with the phosphorus. So they will gain energy and they can easily move to the conduction band, and they will take part in the conduction process. And there will be some electrons which will move from the valence band to the conduction band intrinsically, right? When the bond breaks, so the electron will be released to the conduction band. And when that happens, there will be a hole generated in the valence band. So this we have to remember. And there is one more way in which we can show an N-type semiconductor. Suppose this is our N-type semiconductor, and we can say when the phosphorus loses electron, it will become positively charged. So this is known as the donor core. And I can also show an electron, which is the donated electron. So like this we can show. Now let us see the another type of semiconductor, which is P-type. So here we are using trivalent impurities. Trivalent impurities. So let us take an example of aluminium. So what we have done, we have replaced some of these silicon atoms with aluminium. Now this aluminium has 3 valence electrons. Those 3 electrons will be bonded. It will make bonds with the neighboring 3 silicon atom. And the 4th bond will be having some vacancy. And this vacancy is nothing but the hole, right? So it is having a hole in the, you can see the 4th bond. Now can you see, if we have say 10 aluminium atoms, there will be 10 holes created by that. And there will be some holes which are being generated intrinsically. So we can say in P-type semiconductor, holes are generated first by, you can say we'll be having aluminium, by aluminium, second intrinsically. So can you see the concentration of holes will be large in comparison to concentration of electrons? And again, the concentration of electron will further go down due to recombination process. So we can say in P-type semiconductor, the concentration of holes will be very large in comparison to concentration of electron. And we can say the majority of the holes are due to aluminium atoms. So and these aluminium atoms, basically they are accepting the electrons, and the aluminium will become negatively charged. So we'll call it a acceptor atom. So aluminium is a acceptor atom. So we can say Na is the concentration of acceptor atom. And we can say the concentration of hole will be nearly equals to the concentration of the acceptor atom. And if we want to find the concentration of electron, we can find this by using that intrinsic charge carrier formula. So Ni square divided by Na. So we can use this and we can find the concentration of electron. I hope the concept is clear. Now let us see what is the band diagram for p-type semiconductor. So in p-type semiconductor, we'll be having another energy level created, which is known as acceptor energy level. So what happens? Suppose if we have some electrons in the valence band, these electrons can easily move to this energy level, and then we can say there will be a hole created. So there will be a hole created in the valence band because of this energy level, right? So there will be some holes created because of intrinsic property, right? So when some bonds break, the electron will move to the conduction band and there will be a hole created. And there will be some holes created when the electron moves from the valence band to this acceptor energy level. So you see now again the holes are being created in the two ways, and right. So I think this concept is clear. So we should remember this. And there is one more way to show p-type semiconductor, where we show an acceptor core, right? So this will be acceptor core. And I can also show a hole, right? This is the hole. I hope the band structure is clear to you. Now let us move to the next session. Now let us see how the conduction is happening in metal. So in current electricity, we know that when the charge carrier moves, will define a velocity known as a drift velocity. And this drift velocity is nothing but J upon Ne, right? J upon Ne, where N is the number density of the charge carriers, J is the current density, E is the charge on one carrier, Vd is the drift velocity. And we also know that electric field inside the conductor will be equals to rho J, where rho is the resistivity. And we can also write this as J as sigma times A. Is it clear? So we already know these two formulas. Okay, so and drift velocity. So here I want to find the value of sigma, right? Now sigma is J upon E. And we know one more formula, which is the mobility of charge carrier, which will be drift velocity per unit electric field. So there are three formulas, and I'm going to use these three formulas to see what is the conductivity of a metal. So J upon E is what? So J is NeVd and E is Vd by mu. So we can say it will be Ne mu. So we can say the conductivity of a metal will be given by this formula Ne mu. So you should remember this formula. Now let us see what is the conductivity in semiconductors. So in semiconductor, the conductivity is because of holes as well as electrons. So we can say the total conductivity will be conductivity due to electrons plus conductivity due to holes, and this can be written as concentration of electron times E times mobility of electron plus concentration of holes times E times mobility of holes. So you should remember this formula for semiconductors. Now let us see some illustrations, or let us see some PYQs based on the same formula. So mobility of the electron in semiconductor is defined as the ratio of the drift velocity to the applied electric field. If an n-type semiconductor, the density of the electron is 10 raised to 19 per meter cube, and their mobility is 1.6 meter square per volt second, then the resistivity of the semiconductor. Since it's an n-type semiconductor, contribution of holes is ignored. Okay, so is close to. So we need to find the resistivity of the semiconductor, and resistivity is reciprocal of conductivity. So we should remember this. And we know that conductivity of a semiconductor is given by NeE mu E plus NHE mu H. And we know that in the question we have clearly mentioned that we should ignore holes. So we can take this second term to be 0. If the second term is 0, we'll be having sigma as Ne times mu E, and we can say resistivity will be 1 upon Ne E times mu E. Now let us plug in the values. So Ne is given as 10 raised to 19 E is 1.6 into 10 raised power minus 19. Mu is given as 1.6 in SI units. So this comes out to be 1 upon 2.56, and this is close to 0.4 ohms meter. So C is the right answer. I hope the concept is clear. Now let us see one more example. So here, what is the conductivity of semiconductor conductor sample having electron concentration as this? So this is basically Ne, which is 5 into 10 raised power 18 per meter cube, and hole concentration is 5 into 10 raised power 19 per meter cube, and mobility of electron is given as 2 meter square volt inverse second inverse, and mobility of hole is given as 0.01 meter square volt inverse second inverse. Now we need to find the conductivity. So sigma is N E times mu E plus N H E times mu H. So let us put the values. 1.6 into 10 raised power minus 19. E will be common. So N is given as 5 into 10 raised power 18 times 2 plus 5 into 10 raised power 19 times 0.01. So let us take 10 raised power 19 common. So we'll write it as 1.6 times 1 plus 0.05. So that will be 1.05 times 1.6. So the answer has to be slightly greater than 1.6. So the option A is the right answer, right? 1.68 ohm meter inverse. So we are done with one part of the video where we have covered different types of semiconductors and what is p type, what is n type, and what is the band theory, right? So now let us see what is a p-n junction. Now what is a p-n junction? If we have a p-type semiconductor on one side and n-type semiconductor on the other side, this arrangement is known as a p-n junction. Okay, and how we can form that? We will take a pure semiconductor, and on one side we'll dope this with a pentavalent, and on the other side we'll dope this with a trivalent. So we'll get a p-n junction. So what is happening here? Can you see there is a concentration difference on the left side at the p-type semiconductor? The holes are in majority carrier. So these circles are holes, and these red circles are electrons. So we can say due to this concentration difference, on both sides, on the left side we have large number of holes, on the right side we have large number of electrons. Holes, they move from P to N, and electrons move from N to P, right? So that thing will happen, and due to this there will be a current. So holes are moving from left to right, electrons are moving from right to left. So can you see there is a current which is from P to N side? So this current, let's say this is I1. Now this I1 is known as diffusion current. So I1 is diffusion current. So what happens as the migration starts? We can say there will be positively charged cores, or you can say the donor cores will be left on the N side. So these are donor cores, and these are acceptor cores. Can you see? Now due to this donor cores and acceptor core, there will be a field from the right to left. So there will be a field from the right to left, and due to this field, now it will be difficult for the majority carrier to move from one side to the another. So due to electric field at junction, it is difficult for majority carriers to move from one side to another. Okay. But what happens to the minority carrier? So if we consider a minority carrier, let us say this minority carrier, right? So on the n side we have hole as minority carrier, on the p side we have electron as minority carrier. So if I consider this electron, which is quite close to this region where we have electric field, now what happens? This electron will experience a force in the right direction, and it will be swept away by the electric field, and it can move from the p to n side. Now due to this, there will be another current at the junction, which is known as I2, and this I2 is opposite to I1, right? Now this I2 current is known as drift current, right? So this is the drift current, and it is because of minority carrier, due to minority carriers, right? And the region, this region where I have shown the acceptor cores and the donor cores, this region is known as depletion region. This is known as depletion region. Why it is called a depletion region? Because this region is being depleted of its free charge carriers because of diffusion process. So depletion region, depleted of its free charge carriers due to diffusion process. So greater the width of this depletion region, it will be difficult for the majority carrier to move from one side to the another. So again, we should remember this. Greater the width, more the difficulty for majority charge carriers to move from one side to another. To move from one side to another. Right, so what happens? Can you see as the majority carriers move from left to right? Right, so the field at the junction will keeps on getting stronger, and then again it will offer more resistance to the majority carrier. So what happens at equilibrium? So at equilibrium, I1 balances I2. So we can say there will be no net current. So there will be no net current at junction in equilibrium. When that thing happens, we can say the PN junction has been formed. Got it? So now let us see what is a PN junction diode. So if you provide some metallic contacts at the end, so these are metallic contacts. This is also a metallic contact, right? So why we provide metallic contacts? So that we can connect this PN junction with an external source or with a battery, and with that battery we can alter the electric field at the junction. So let us see a very basic case when there is no battery connected. So there will be some potential difference at the ends of the depletion region, right? So let us say this is delta V. Now, if I show this on a graph, so let us say at the P side the potential is 0, and then it increases, and then it stabilizes, right? Let us say like this. Now this height is delta V, and it is known as potential barrier. Now, if a majority carrier has to move from one side to the another, it has to surpass this barrier. So we can say it should have some minimum energy, and that will be nothing but the charge times the barrier potential. So that is the minimum energy required to move from one side to another by majority carriers, right? Okay. So what would happen if we say uh, connect the diode or connect the junction with a battery? So before that, let us understand like how to show PN junction diode in a circuit. So the symbol that we're going to use is a triangle with a vertical line. Now this triangle side is the P side and this vertical line side is the N side. So you should remember like this, PN. Now if we connect the P side with the high potential of the battery and N side to the low potential, then this type of a connection is known as a forward biasing. So let us consider let us study what is forward biasing. So forward biasing is when we connect P side to a high potential and N side to a low potential. This is N, this is P, right? This is positive and this is negative. So what would happen? So we know that at the barrier or at the junction, there is an electric field which is in the left direction. Let me call it E. Now, because of this external source, now there will be an external field in the right direction. Now, what happens due to this field? So, this external field will reduce barrier potential. So, we can say due to E external, field at junction decreases, right? So, if that decreases, so let me redraw the diagram. So when the field at the junction decreases, so there is a, we can say a field E and there will be an external field E external in the right direction. So what happens now, it will be easier for the holes to move towards the N side and will be easier for the electron to move towards P side. So what happens, the width of depletion region decreases, right? Because now it is easier for majority carrier to again move from one side to the another. So that is the case when we have a battery connected like this. And this is P and this is N. So what we can say, if we show the same, on the same graph, if I show the graph for forward biasing, so this, let us say this will be delta V1. So here, let us say this is delta V1, right? Now there is another type of biasing which is known as reverse biasing. So in reverse biasing, the diode, the P side is connected to the low potential and the N side is connected to the high potential. Now, can you see the direction of the external field? So external field is in the left direction, which is in the direction of the field at the barrier. So in this case, in reverse biasing, if I again show the diagram, the depletion region width increases. And it will be difficult for the majority carrier to move from one side to another side. So if I connect this with a P side to the low potential and N side to the high potential. Now there is a external field which is in the left direction, and the field at the barriers again, it is in the left direction. So if I show, if let us say the potential difference now is delta V2, so this can be shown on the same diagram. So I can show it like this. This will be delta V2. Now it will be even more difficult for majority carriers to move from P side to N side, right? But what happens in this case? But in this case, this field will assist the motion of minority carrier. Suppose if there is a hole in the N side, suppose if this hole is moving randomly in the N side, if we come close to this depletion region, now this hole will be swept by the field and it can move to the P side. So we can say in reverse biasing, there can be a current because of the minority carriers. But in the forward biasing, there will be a current because of the majority carriers. So that's why the current in forward biasing is the order of milliamperes. So in forward biasing, the current is of the order of milliampere, but in the reverse biasing, it is of the order of microampere, nearly 1,000 times lower current. Because in reverse biasing, we have minority carriers which constitute the current, but in the forward biasing, we have majority carriers. So we have to remember these points in mind. Now, if let us say see the case of an ideal diode. So in case of an ideal diode, we can say in forward biasing, the resistance is nearly zero. So we can say the diode is conducting in forward biasing, and in reverse biasing, the resistance will tends to infinity, or we can say it will be a perfect insulator. There will be no current. There will be no current in through the diode. It will behave like an open switch, right? So I hope this concept is clear. Now let us see the VI characteristic of a diode. So what is the VI characteristic? Right. So we have seen the forward and the reverse biasing. So so what we're going to do, will alter or will change the potential difference applied across the diode. So in the forward biased mode, as we increase the voltage, can you see initially there is no change in the current? There will be no current in the circuit, but suddenly at a particular value, the current increases drastically in the forward biasing. And this current and this voltage, this voltage is known as knee voltage. So we can say, what is the knee voltage? Like beyond knee voltage, the current increases exponentially. And this knee voltage for silicon is around 0.7 volts. And for germanium, it is around 0.3 volts. So these values you should remember. And can you see now we have a non-linear graph. So it's a non-linear. So here we'll talk about a dynamic resistance. So dynamic resistance in forward biasing will be given by delta V upon delta I. Let us say there are 2 points on the graph, and usually we measure dynamic resistance beyond knee voltage. So let us say this is point number 1, this is point number 2. So if I measure this value, so this will be delta I and this will be delta V. If we take the ratio of delta V to delta I, we'll get the dynamic resistance in the forward biased mode. And now let us see what happens in the reverse biasing, right? In reverse biasing, can you see there is some constant current, and suddenly the current increases at a particular voltage. Now this voltage is known as the breakdown voltage. So at the breakdown voltage, the field at the junction will be so large that the field emission starts to act. What is the field emission? The bonds will break in a large number, and there will be huge amount of current at the junction, right? So we can clearly see that at the breakdown region, we have a different values of the current for nearly the same voltage. And this constant current in the reverse biased mode, this constant current, let us say this current is I naught, or we can let us say this I naught. This I naught is known as reverse saturation current, and it is of the order of microampere that we have to remember. And breakdown voltage, so at breakdown voltage we have a range of values of the current, and usually it is recommended by the manufacturer of the diode that we should operate diode not beyond breakdown region, says up to this particular volt, right, which is less than breakdown voltage. So this nature we have to remember. And suppose if I want to find, let us say in the reverse biased mode, the reverse saturation current is attained, say when the voltage is V0. So what we can say, the resistance in reverse biasing will be V0 divided by I0. Got it? So these points we have to remember. Now let us see the types of questions which are being asked from the diodes. And just remember one more thing, in case of ideal diode, in the forward biasing it is conducting, in the reverse biasing it will be non-conducting. So let us see a typical question. So when a diode is forward biased, it has a voltage drop of 0.5 volts. The safe limit of the current through the diode is 10 milliampere. If the battery of EMF 1.5 volt is used in the circuit, the value of the minimum resistance to be connected in series with the diode so that the current does not exceed the safe limit. Okay, let me draw the circuit here. So we have given a diode in forward biased mode. So it means the P side is connected to the high potential and N side to the low potential. And we have connected this diode in series with a resistor, and there is a battery and of voltage 1.5, and we need to find the value of the resistance to so that the current in the circuit does not exceed 10 milliampere. And we have also given one more thing, when this diode is conducting, there is a potential drop of 0.5 volt across it. And let us say this is R, right? So to find the minimum value of the resistance, we'll assume the maximum current in the circuit. So let us say the current in the circuit is 10 milliampere. Now for this current, the potential drop across the resistor will be nothing but 1.5 minus 0.5, so that will be 1 volt. Now through this resistor there is a current of 10 milliampere. So by Ohm's law we can say the resistance will be 1 divided by 10 milli, right? 10 raised to minus 3, so it comes out to be 100 ohms. So the resistance, minimum resistance required to operate this diode will be 100 volts, 100 ohms. Now let us see another question. So the current I in the network. So we have given 2 diodes and 6 resistors and a battery like this. So can you see the N side of the diode is connected to the high terminal, right? And the P side is connected to the low potential. So we can say both these diodes are reverse biased. So they are in reversed biased mode. So when that is the case, and if nothing is given in the question about the type of diode or like whether it is an ideal or real diode, you should always treat it as a ideal diode. So in ideal diode, in reverse biasing, it behaves as open switch. Okay, right. So if I redraw the diagram, so I can show diode as an open switch, and the resistor will be as it is. So we have a diode as an open switch, and then we have a 5 ohms resistor and a battery. So we have this circuit diagram. So this is a 9 volt battery, 5 ohms resistor. This is 10 ohms resistor, 5 ohms, 5, 10, 10, 20. So if I show the direction of the flow of current, so current will flow like this. It will not pass through the open circuits. So can you see now this 5 ohms and this 20 ohms are not contributing anything, so we can remove them. So the current is flowing in a path which is having a resistance of, let me add up all these resistances, 10, 5, 5, 10, so around 30. So we can say the current, let us say the current is I. So I will be 9 divided by 30. So that comes out to be 0.3 ampere. So option C is the right answer. Now let us see one more question. So in this question, we have given two identical capacitors A and B charged with the same potential of 5 volt are connected in two different circuits as shown in below at time t equals to 0. If the charge on capacitor A and B at time t equals to CR is QA and QB respectively, then, okay, right, so we need to find the value of QA and QB at t equals to CR. Now let us see the first case. So in the first case, we have a charged capacitor and the positive plate is connected with the N side and the negative plate is connected to the P side. So we can say this diode is reverse biased. If it is a reversed biased and nothing is given about the diode, so we'll treat this diode as an ideal. So if it is an ideal diode, then it is acting like an open switch. So in the first case, there will be no discharging, right? So if there is no discharging, we can say the charge on the capacitors will remain as it is. So it will be CV. So in the first case, QA is CV, where C is the capacitance, V is the potential difference across the capacitor. Now in the second case, so in the second case, the positive plate is connected with the P side and the negative plate is connected to the N side. So we can say this diode is forward biased. If it is forward biased, there will be a current. And now we have a RC discharging circuit. Now there will be a current in this circuit. So in the second case, it acts like a RC discharging. And in RC discharging, the charge on the capacitor will be the initial charge times e raised to power minus t by RC, right? So that is the formula that we use for discharging. So at t equals to CR, we can clearly see that the Q value will be CV e raised to power minus 1, which will be CV by E. So can you see which option is correct? So option C is the right answer. Okay, so this type of questions are being asked. And there is one more type of question which is based on the VI characteristic. So about the resistances, dynamic resistances. So let us see. The VI characteristic of a diode is shown in the figure. The ratio of the forward and the reverse biased resistance is. Okay, right. So in the forward biased mode, how to find the resistance? I told you like we have to take 2 points on the graph or any 2 points, right? So let us take, say this point is A and this point is B. So now find the current, right? Change in the current from A to B. So it will be 20 minus 10. So it will be 10 milliampere. Now let us see what is the change in the voltage from A to B. And this will be 0.1 volts. So the resistance, let us say R1 is the resistance in forward biased mode. So that will be delta V upon delta I, and delta V is 0.1 and delta I is 10 milliampere. So this comes out to be how much? So we have 0.1 divided by 0.01. So it will be 10 ohms, right? So in the forward biased mode, we have 10 ohms resistance. So in the reverse biased, we have given minus 10 volt for the reverse saturation current to be achieved. And the reverse saturation current is given as 1 microampere. So we can say the resistance in the reversed biased mode will be 10 divided by 1 microampere. So 10 raised to power minus 6. So it will be 10 raised to power 7 ohms. And we have to find the ratios. So R1 by R2 will be 10 by 10 raised to power 7, which comes out to be 10 raised to power minus 6. So option B is the right answer. So I hope you know how to tackle such questions in exam. Now, let us see another application of diodes, and that is the rectification of AC signal. So if we have a AC signal and I want to convert that into DC, so the same thing we are doing with our charger, right? So we feed in the AC supply coming to our household and convert that supply into a DC supply that charges our mobile phone or our laptops. So rectifier is a device which converts AC to DC, right? So here we're going to study three types of rectifier. One will be half wave, then second will be full wave rectifier, and third will be full wave with capacitor, filter. Now let us see one by one. So first we'll see what is this the circuit for this, and then we'll see how that circuit works. So in half-wave rectifier, we'll be having a alternating source, and this source is being connected with a transformer. So this is the primary winding of the transformer, and this is the secondary winding of the transformer, and there is a diode, a single diode, right? A single diode connected like this, and there is a resistor. Let us say this is our load resistor, and this is the primary winding, this is the secondary winding. Okay, so now if the top side of the primary winding is at high potential and bottom is at low potential, then we can say that the top will be in the secondary, it will be at high and it will be low. So when this thing happens, so when we can say in the positive half cycle, so in the positive half cycle, this is our input voltage. The P side will be at high potential, the top side will be at high potential, bottom will be at low potential. Similarly, by mutual induction, the S will be at high potential, the top side of the secondary will be at high potential and bottom will be at low potential. Then we can say the P side of the diode is connected with the high potential. So this diode is forward biased, right? So it will be forward biased. So if the diode is forward biased, then it will be conducting. So there will be some current through this load, and we will measure this potential difference. Now this is the output voltage. So can you see we'll have a reading, right, when the diode is forward biased. Now if you talk about the second half cycle, which is the negative voltage, then we can say the top side of the primary will be at low potential, bottom will be at high potential. Similarly, by mutual induction, the secondary coil, the top side will be at low potential, bottom will be at high potential. In that case, the diode will become reverse biased. Now the diode is reverse biased, so it is non-conducting. So we are considering a case of an ideal diode. So it is non-conducting. So if it is non-conducting, there will be no current through the load resistor, so there will be no reading. So we can say if I plot the graph for output, it will be like this. So for first half cycle, we'll have a reading, or we have some output voltage, and then it will be 0. And then again for the third half cycle, it will be positive again, and then will be 0. So can you see what is happening here? We are able to rectify half of the wave, right? But not the full wave, because we are not able to rectify the second half. That much portion is not, we are not able to rectify. So that's why it is known as a half wave rectifier. And you should also remember one important point about the half wave rectifier, and the derivation of that is not that important. You should remember that the efficiency of half wave rectifier is close to 40%, right? Considering the losses and all those things. So it is close to 40%, that you have to remember. Now, let us see a full wave rectifier. So again, we'll feed us AC supply to this rectifier, and again we have a transformer, but now we are having a special transformer. It is known as a center tap transformer. In center tap transformer, the secondary winding is made up of two parts. So we have two coils in series, and there are two diodes. Let us say this is diode D1 and there is a diode D2, and they are joined together. Their P sides are joined together, and from the center of the secondary winding, there is a load resistance. So this is RL, and we are measuring the voltage across these 2 points. So this is our output voltage, and this is our input voltage. Again, here what is happening? So we have a sinusoidally varying input voltage. This is input voltage, and in the positive half cycle, the top side of the primary will be at high potential and the bottom will be at low potential. Similarly, we can say the top side of the secondary will be high potential. So if now it is made up of two parts. So for the first part, the bottom side will be at low, and again for the bottom half, the top will be at high and the bottom will be at low. So can you see what is happening here? So the D1, it is connected with a high potential, so we can say D1 is forward biased, and D2 is connected with the low potential, so D2 is reverse biased. So what is happening here? So there will be a current through the resistor like this. So there is a current and we'll have some reading. So we will be able to rectify first half wave. So if I show it on the graph, so we are able to rectify a half wave, and this is because of the diode D1. This is the output voltage. Now, if we talk about the second half cycle, the top end of the primary will be at low potential, bottom will be at high potential. Similarly, the polarity will also reverse on the secondary side. So the top will be at low potential, then plus, and then minus, and then plus. Can you say now the diode D1 is reverse biased and the diode D2 is forward biased? Now when diode D2 is forward biased, it becomes conducting and D1 will become non-conducting. So now the current will flow like this. Can you see even in the second half cycle, the direction of the current is same through the resistor. So we'll get this output. Can you see? And this output is because of D2. Similarly, for the next half cycle, we'll again able to rectify. So this is D3, sorry, again by D1. And then for the fourth half cycle, again we'll get rectification. So this will by D2. And again, remember one more thing. So the efficiency in case of a full wave rectifier is close to 80%. So do remember this, because there was a question in JEE where they have asked this, what is the efficiency of a full wave rectifier? So you should remember this, right? So now what is a rectifier with a capacitor filter? So can you see in both the rectifier, whether it is a full wave rectifier or a half wave rectifier, we are getting a rectification, but the voltage is not regulated. It is unregulated DC voltage. It just keeps on changing, right? But its direction is not changing. So to overcome that problem, we will use a capacitor filter. So let me draw the circuit first. So there is a AC source, and this is the primary winding. And again, we have a center tap transformer, right? So the secondary is split up into two parts. And there are diode D1, and here we have diode D2. D1, D2. And the load is connected like this. And and we have connected a capacitor in parallel to the load. And we are measuring the output voltage across the capacitor. Now, what would happen in this case? In this case, as the current flows through the resistor, the capacitor will also get charged. So if the input voltage is sinusoidal like this, in this case the output voltage, it will increase, right? Let us say it increases, and then after that it will be nearly, we can say, remains constant. The reason for that is when there is no current, or when the current decreases, let us say, in that case there will be a discharging of the capacitor. And when the capacitor is getting discharged, what would happen? It will not get discharged instantly. It will take some time. So when it takes some time, suppose if we decide, if we set, suppose if we choose the value of C and RL such that the time constant is really high. If the time constant is really high, so the capacitor will take a large amount of time to get fully discharged. So if we consider if we take time constant to be large, in that case, it will discharge by a small amount, and again we can say the current will increase, and again it will get charged. So the cycle, so we can have nearly a constant output. So here we have nearly the constant output. So can you see? So with the help of the capacitor filter, we can regulate the DC output supply. I hope it is clear. So here I conclude this video. So wish you all the best for your exam, and I'm pretty hopeful you will pass your exam with flying colors. Thank you.